While the vector model is really great at modeling discrete geographic phenomena, it's not very good at modeling continuous geographic phenomena. For that, we typically use the raster model, which models geographic objects as cells arranged in columns and rows. And those rows and columns are located on a Cartesian coordinate system. If you look in the example on the lower right-hand side, you can see I have a Cartesian coordinate system. This time the origin is in the upper left-hand corner, and then the rows and columns are laid out in a tabular matrix. Now, each pixel or cell has the same height and width. And because I know the height and width of the cells and I know the number of columns and rows, I can lay the raster data out in space. Now, each cell in the raster model can include a value, and it might be a whole number like an integer or a decimal number like a real number. Additionally, cell values can be identified as having no data. This is important because sometimes when you're representing a continuous phenomena like temperature, you might have temperature data for a large portion of your area of interest, but there might be some area where you weren't collecting data. So rather than making up the data, you can assign the value as no data. Now, because raster model is laid out on a Cartesian coordinate system, you can transform it to a geographic coordinate system. And if you look over on the right-hand side, you can see where we've taken a basic raster data set with a number of rows and columns with cells 100 width by 100 height are laid out on a geographic coordinate system. So now they're located in geographic space. And in this case, the cell values represent land cover, grass, forest, or water. Now, each raster cell is linked to a corresponding attribute value. The cell geometry is stored with a list of values in a floating point decimal raster or separately in a table in an integer raster. On the left-hand side, you can see a floating point raster in which every cell has a value, but because it's a floating point or a decimal raster, the list of values are just stored in a corresponding line of text. So for example, if we start in the upper left-hand corner and then work our way from left to right, you can see in the list of cell values, the first one is no data, then 3.1, 3.3, 2.7, and so on. Integer rasters store values whole numbers, and the values are stored in a corresponding table. And so if you look at the example on the right, you can see that we're mapping land cover, forest, water, cropland, urban area, no data. And the underlying integer values correspond to a type of land cover. So for example, 1 is forest, 2 is water, 3 is cropland. Because those are whole numbers, the data is managed in a corresponding attribute table in which you can see, for example, the very first record says value 1, there are 5 cells and their type is forest. So it's a little bit different than the vector data model in which each feature represents a record in the table. In the raster data model, all of the cells of the same value are represented as a single record in the attribute table. In this case, for example, forest. Some of the pros and cons associated with the raster data model include advantages like it's easy to understand and easy to read and write and easy to display because it's just rows and columns and values. So the raster format has not evolved or changed as much as the vector format over time. It's very good at representing continuous surfaces. So for example, like temperature or population density or soil pH. And it's a natural for scanned or remotely sensed data, for example, like satellite imagery. The disadvantages of the raster model include it's very poor at representing discrete point lines and areas because it generalizes those discrete objects and makes them look square. The raster model includes redundant or missing data. Because your area of interest is represented by a large rectangle, you might have some areas that you're not really interested in, or there's data missing, but you still have to include it in your model. And then each cell must pay the storage price for the highest value cell. So if you have one particular cell where you need to store a decimal, then all of the cells have to store decimals. Here's a list of raster data sets that we utilize in ArcGIS, starting with the simple geodatabase object, a raster data set, in which we can create, delete, read, and write these in ArcGIS. A raster mosaic allows us to tile a bunch of raster data and represent it as a single layer in ArcGIS. So for example, if I have a city that has 100 high-resolution images of the city, I can tile those in a raster mosaic, and then bring that in as a single layer rather than having to load all 100 images into my GIS to view all the imagery for the city. A raster mosaic is also very nice because I can process all the tiled raster data as one. So for example, I can perform some type of transformation or conversion process and do it on a single layer rather than the 100 images that I mentioned in my previous example. A raster catalog is just an older version of a mosaic, but you can only view tiled raster data. You can't process it. An ESRI grid is an older raster format that exists outside the geodatabase, but in ArcGIS we can create, delete, read, and write, and we'll often work a lot with ESRI grids. In some ways, it's kind of like the vector version of an ESRI shapefile. It doesn't exist in a geodatabase, and it's really easy to work with, so sometimes we'll work with grid rather than a geodatabase raster data set. Other raster dataset formats that we work with in ArcGIS include the tagged image file format, a portable network graphic, and even ArcGIS Online raster layers. But those typically are just read. We can't actually process those datasets unless we import them into a raster dataset or grid.